So, we can continue with infinite horizon problems. We have seen finite horizon problem, we have seen deterministic and stochastic. Now we will extend that to infinite horizon. So these are the things we would like to discuss. An infinite horizon problem, as the name suggests, it will continue forever. Okay, there is no finite number of times given up to which it has to continue, but rather it will. There is no certainty that it will stop. We need to model these problems. So one possibility that we saw is that we can take these n tends to infinity. So take finite horizon, but then n tends to infinity. So this is like finite horizon, but then so for a fixed n it's finite horizon, but then if we take n tends to infinity, then it allows us to kind of take larger values of n. So this is one possibility, but as we know, when we work with sequences which are infinite sequences, in this case is a series, and it's not a finite series obviously, because as n tends to infinity, then one of the things that we worry about is whether this will converge. Okay, because if this quantity itself goes to infinity, then you cannot really work with such quantity, right? So the moment we go into in infinite series and stuff, then we don't want this to accumulate and go. So if we want to implement this as algorithm, then we know that we can only store some largest real number, right? And beyond that, we cannot really store them in computer, right? So basically this quantity should not go grow too much. Okay, so in infinite horizon, these are the issues we have. So you will see now that there are now this quantity alpha k involved, which was not there in the finite horizon case. So alpha k can help with that. So now we know that this is a reward. Okay, g xk uk. So this is the current, I mean not the reward, but let's say the cost to go from k to k plus 1 and so on. And so now alpha to the k will kind of, depending on the values of alpha k, we decide whether my current cost needs to be weighted more than the cost that was like long time ago. Okay, so if alpha is between 0 and 1, then you kind of give more importance to the current for small values of k. For smaller values of k, the quantity will have higher weights, but as k goes to infinity, the cost g xk uk will go towards 0. So so this is about alpha k. So basically we call this a discounted reward or cost if alpha is between 0 and 1. So and here g is our cost to go, obviously, and as we have used f before, we can also think of xk being produced from f xk uk. So this is about infinite horizon. We can take finite horizon and take n tends to infinity, then it's like infinite horizon, but then we worry about the series itself, because it's infinite series. Then we may take alpha k, and then and between 0 and 1. So technically it with alpha k going to 0, it's a series that it's finite, and then g and f is as usual. So we assume that f is kind of fixed. So f is not changing with states. So f is the same f, but depending on xk uk, it will produce different outputs. So the stochastic disturbances, so this is still stochastic because we keep these wk terms, which are random variables, and we for all of these we expect that they come from some common probability distribution. So the PDF of these w0 to the density function is the same. Okay, again you can wonder, is it possible that the disturbance at k comes from some distribution, let's say Bernoulli, but then disturbance at k plus l comes from some other distribution like binomial or something. So there is a possibility to complicate this more, but we may assume that they come from the same distribution P. So this is the infinite horizon setup. Um, so um, um, so let Jn denote the optimal cost of the problem involving n stages. The notation is the usual one, and cost per stage is Gx uw, and we assume zero terminal cost, let's say. Then the cost generated after n iterations, we can write it like this. So at the kth iteration, so this will be the cost, and so this we call it a value iteration. Okay, so at the kth step, the cost at the kth step, which is very similar to what we have done in the finite horizon. So this is the cost that we get in the infinite horizon at the kth step. Okay, that's all what we did. So now the question is, what could be our optimal cost J star for infinite horizon case? Okay, so again, the only thing to keep in mind is that this is a infinite series. Okay, so what could be J star in that case? So the optimal infinite horizon cost, as we know, the way we define the cost will be limit n tends to infinity of J n x. Okay, so this is how we'll get the infinite horizon cost. And then the following equation should hold for all states x. So that J star, the optimal infinite horizon cost, will be written like this. So where we have the cost, the current cost, plus the cost that we have for the future. Okay, so this is what we call is a Bellman equation, and this the reason for this, the writing in this form, is that we want these this J. So since this is a infinite horizon, we expect that this sequence of Jn will ultimately converge to some J. Okay, so I can think of these as sequence of functions, and they converge to some J star. Like this is what this means. As a sequence, it goes to some J star. Yeah. So let us see some remarks on Bellman equation. So Bellman equation is actually a system of equations. So for a given x, you minimize for the control. Okay, so for all possible x, it's like a sequence of optimization problem for a for x. Okay, so it could be seen as a sequence or system of optimization problems. If ux attains the minimum on the right hand side of Bellman equation for each x, then the policy that we will obtain will be called optimal policy, and we also call it like a stationary policy. So if we can solve this Bellman equation, then the u that we get, which is by applying the policy. So the u in our case is nothing but mu applied on x. So without any confusion, sometimes we say control and sometimes we say policy. So whatever u that we see here, it could also be written as ux, mu x. So if we can solve this for all x, then the mu that we get is called stationary policy. Okay, so the cost function J mu for stationary policy mu, assuming that we have solved the optimization problem, Bellman problem, then the cost function could also be written in this way. So basically the controls are given by the stationary policy that we have. Okay, so this is the cost that we saw. We can view above cost as just the Bellman equation for a different problem. So for instance, for each x, the control constraint ux we can think of as just containing one control mu x. Okay, so and we also expect that J mu is obtained in the limit by as this way. Okay, so we expect that this cost with the stationary policy mu is obtained by limit n tends to infinity j mu n. So and j mu n again could be written in this way, where you have, if you want to see this in terms of uh, stages k and k plus 1, then we can write it in this form. So okay, so there are algorithms that we will see in future, and I can skip the like equivalence with the nth step like this. Not really. Yeah. So the question is, can we have seen value iteration. Can we also run iterations over policy, which is mu? So we can write down a policy iteration which also involves two steps, which is policy evaluation and policy improvement. So what are the advantages of running iterations on policy? Well, it will help us use so-called self-learning. Basically, it will help us use neural networks. So generate some data and then use that in policy iterations. So anyway, we will come to that. Like, well, this right now is not very evident. So let us see what policy iteration is. We saw value iteration. Now let us see policy iteration. So basically, we have a base policy, and there is a way to let's say evaluate the current policy, which is j mu, and then we improve on the policy. Okay, so and we keep iterating this. Once the policy gets updated, we evaluate and so on. Like, this looks very similar to the way we use look ahead and roll out. It's just that the view is in terms of policy now. So it's not like we have a base policy, we do look ahead, roll out, and then our policy improves and so on. So this is, it's very similar. It's not. It's just that now we write down in terms of policy iterations. So what goes in policy evaluation is, so in policy evaluation we compute the cost j mu of the current base policy, and we can do this by solving the Bellman equation, or we can apply some Monte Carlo simulation, especially when I mean, in most cases we have to apply Monte Carlo simulations unless we know explicitly about this W. So this would mean that we will generate a lot of samples, W samples, and this will be useful in having an expected value of this quantity, right? So stochastic makes our work a little bit more involved, because we are supposed to compute this expectation over the random variable W, and this very likely you will go do it by doing some form of averaging. So sample various W's at the current X, and then because once you sample, then it becomes a deterministic kind of thing. So once you sample, then this will be G X mu X W1 plus alpha J mu and so on, right? And this becomes another G X mu X for W2 and so on. So these you take the average of these, right? And then obviously the other things, the estimates given this disturbance W1, which after sampling you got some fixed values, and then you do the remaining cost estimates with the current policy J mu. You do this, compute this value, and then for W2 you do this estimate of J mu for another W, and so on, and then take the average. So and then policy improvement is obviously the policy if in case it gives me a better value, in the sense like it minimizes more, it minimizes the cost more compared to the base policy, then obviously we are going to use the mu tilde, which at best it will be as high as the current base policy. If not, then we are improving, so it will be strictly less. Okay, and this is something we have also seen previously in the look ahead and rollout case, where we have a greedy policy, but then when we explore, then we do better than the greedy policy, then it's fine. Otherwise, we stay with the greedy policy. So, because we improve our policy only when we minimize. So, because of this argument thing, so we will not be doing worse anyway, because that's how everything is set up, right? So, so this is the policy improvement. Um, so overall, the idea is kind of very similar. So you have some way to evaluate the policy, which is like JMU, and then you do policy improvement. So you keep doing this repeatedly, like in this. So this is the policy iteration algorithm. So you need some base policy, obviously. So this is very similar to what we have done before. It's just that now we are in an infinite horizon case. So rollout algorithm and policy iteration, this is what I have been saying. So rollout algorithm in its pure form is a single iteration of policy iteration algorithm. So actually we have done this before. Rollout algorithm is nothing but policy iteration. So and then a few other things we can point out. So it starts from a given base policy and produces a rollout policy mu tilde. It may be viewed as an approximation in the value space with one step look ahead. So all this we know. The approximation uses JMU as the terminal cost functions. So all this we know. So basically cost with the base policy. So if we were working on traveling salesman, then we had a base policy which was greedy, and that gave us JMU. So it's the same thing here. So rollout algorithm has the advantage that it can be applied online. So that also we know. The needed values of JMUX can be computed by simulations. So that's also we know by now. So basically we may run some trajectories and then take the average. In the stochastic case, obviously. So and in general, approximate forms of policy iteration for challenging problems like Atari game or any like chess game or Go or all this, they definitely involve neural network training because then you need to do some kind of a good feature extraction, and because the state space and all this is huge. So so in case you do plan to use neural network type, then it will be very likely offline, because you might need to kind of have you might have to generate some data, state action data, and then you might do it fit a neural network offline, because the data itself maybe you will generate will be huge, and then you may want to train neural network first on those type of data, and then you can you can use the cost JMU, right? So in that case, JMU will be neural network will be predicted by neural network. So there will be a theta parameter there, which will be a neural network parameter. So typically it will be offline because training neural network might will involve some time, right? And it also needs a lot of data. So approximation in the value space in the infinite horizon case. So approximation in the value space for infinite horizon for finite horizon can be extended to infinite horizon. So again, same way. So instead of J star, we use J tilde. At any state x, a control mu tilde can be generated using look ahead minimizations, and this minimization will lead to some stationary policy mu tilde. So here, what is different from finite horizon is that we generate this so-called stationary policy, and with a cost function J mu tilde, and if it so happens that the cost generated with stationary policy mu tilde, as you like do this repeated iterations, if it so happens that J tilde becomes equal to the optimal J, then there is a proof that we can prove that it will satisfy the Bellman equation. Such J tilde will satisfy the Bellman equation, and it will be the optimal one. So obviously aim is to get J tilde as close to J star as possible. So this is what we want. We want J mu tilde close to J star for optimal for effective control. And if we work on classical control problems, then stability of the policy mu tilde becomes a primary objective, and we will see that in detail with an example, like what does it mean by policy being stable, right? So like what is the intuition behind policy being stable, right? So we will see that what stability of policy means. So intuitively, we can, I mean, in general, we can define a policy to be stable, which does not blow up the cost value, basically. So policy is stable when, like, the cost corresponding to that policy is finite, in a broad sense, right? Um, so, so deciding on J tilde um, to ensure the stability of mu tilde is of significant interest in control theory and predictive control. In control theory, we will look at in detail with one example. The quadratic control problem we will look at again, and what value iteration and policy iteration looks like in specifically for one example. So now L step look ahead for infinite horizon, how it will look like. Well, this is similar to what we have done before. So only thing, one of the things you notice is, like, we don't have these, like, k sub k or anything showing up now, because we expect that they have converged to some j, right? That the limit n tends to infinity jn in limit converts to some j. Okay, so that's why you don't see this k showing up in these, because we are working with this converged like sequence, the converged function j tilde. So in infinite horizon case, the one step look ahead will be like we minimize this, the current cost, and then the cost given by j tilde from there onwards. Okay, so and this f that you see here, the way we define f is gives me the next state, right? So j tilde is applied on the next set of states. Okay, so current cost, and then the next says the cost from next state onwards is j tilde. Okay, and since there is no kind of so this is our one step look ahead in the infinite horizon case, and then if we want to do multi-step look ahead, then we will create those L steps, which is like k to k plus L, and then the remaining ones are given by j tilde k plus L onwards. So this is our L step version, which is similar to what we did before. This is cost to go, the current the current cost, and then these are the sum of the discounted cost up to k plus L, and then this is for the remaining, for the future. So we do L step look ahead, and then add the remaining cost from L plus 1 onwards. So this also works in the infinite horizon case. The only thing is that we have some j tilde in hand, which could be corresponding to some base policy, because we don't know j star anyway. So we don't know j star anyway. So we will be always working with some j tilde to which is an approximation of j star, and we can do one step look ahead, which is the usual form, and then we can also do multi-step look ahead. At state xk, the objective is to minimize the cost of the first L minus 1 stages, with feature cost being approximated by j tilde. So this is the feature cost section of this, and then this is where we look for the minimum possible cost up to L, from starting from k to k plus L. So we are looking for minimum possible cost between stages k and k plus L, and obviously we cannot do it until the end, because that's like not feasible. Okay, because even in L step look ahead is very costly. We have seen traveling salesman problem, because there are choices that keeps increasing kind of exponentially. So L step is only you can hope for. Obviously L step is much costlier than one step. So the minimization process results in control uk tilde, and the sequence for the current optimal k control, and then k plus 1 to k plus L minus 1 controls. So these are the optimal controls we get after L step look ahead. So Um, so after doing the L step look ahead, the control that minimized the current, the control that gave me the minimum value for the L step look ahead is what we will take as an updated policy, the L step look ahead policy. So um, this is what we will take, which will minimize this L step minimization problem, and the subsequent controls are discarded, right? That's what we do in multi-step look ahead, right? So although we minimize over all this um, L controls, but the only control we take is the current optimized one, which is mu k, and we discard mu k plus 1 to k plus L. Okay, this is what we do in L step. It's not like we take all those mu to mu L k plus mu k to mu k plus L and optimize the and take all those controls from k to k plus L as the optimized one. We don't do that. We only do that for exploration, but what we really update the policy is for the kth step, right? So we are clear on that, because this is what we also did in the traveling salesman problem. Is look ahead is only about taking your next optimal step. Now you do one step look ahead, you still take take the optimal action for the current step. You do L step look ahead, but you only do out of the L step look ahead. It helps you determine the best current action. Okay, but it doesn't mean that the next set of actions or the controls are still optimal. No, that was only used for look ahead. But what you will use to update your policy is only the current control, mu xk, or mu tilde applied on xk. Okay, so look ahead, you are allowed to do as much as you want to explore, but you will only do the best action for the current moment. Okay, this is what is the way we define look ahead. This is what we do. Now you may go ahead and do approximations and say, oh, look, I have explored 100 steps. Why should I only, out of 100 steps exploration, why should I only take the first step and then I go to the next step and then I do again 100 steps exploration in future? So you may say, maybe let me jump 2 steps and then explore 100 steps. So that's up to you. But the way we define multi-step look ahead is only helps me for the current control. Okay, so that's why you see this discarded. Okay, it was useful for my to take the current step, but I may not need that. But when you write the code, maybe you can store them in some way. This is some interesting information which you may use, but it is disregarded in the sense that I'm not using mu tilde k plus 1 that I found now to decide on k plus 1. No, I will do look ahead again from there onwards, because they are not necessarily going to be optimal. That's the problem. Okay, when you do L step look ahead, it doesn't mean that the controls up to L are optimal. That's the point, right? You can think about traveling salesman problem. You can work out this. I may create one assignment for you. You may see for yourself. So we will disregard, and so obviously L step look ahead minimization can be seen as an instance of one step look ahead method. So one step, we are doing it one step at a time, but here we have like bigger window. So yeah, we may think of these as kind of a problem that kind of terminates in L-1 stage and so on. I mean, this is another view, but not really necessary. But what this is trying to say is like this is the look aheads, let us say, and this is the Lth step, right? And this is our kth step. And then from there onwards, obviously the problem keeps going onwards, right? So we don't really. So this is like a small DP problem in itself. This is what it's trying to say. The L step look ahead is basically as if like you forget everything that's going to go. So as if you're solving a smaller sub problem, smaller DP problem where your algorithm terminates at the lth step, right? So it's a view. So it could be seen as a L minus 1 stage DP problem. Okay, so this could be seen as like the cost for L minus 1 stage DP problem. Okay, but I don't know how this is going to help for because we are working with infinite horizon anyway. Okay, so the incentive so L step look ahead we have seen already, and this is again we are repeating for the infinite horizon. So the motivation is very similar to what we know already. The incentive behind L step look ahead minimization is that by augmenting the value of L, a less precise approximation of J tilde might be necessary. So why would you do L step look ahead? Because you think that your current estimate is not that good. Okay, so let's say you are preparing for some competitive exams like let's say GATE exam or NET exam, then your current estimate of J tilde is your success in these exams. But then and one possibility is that you cover some topics for the exam, and but then your estimate of your success or failure is not really like very solid. Then in that case you will be more agile and you will say, okay, no, I know what are the things I'm supposed to do, but let me explore, look at various published question papers and patterns and things like that, and let me explore. So this will be like your look ahead. You are kind of looking for various sources to understand more about this, and then although you can do only one step at a time, so you can only study one topic at a time. So so L step look ahead is when you are not very good with the cost estimate J tilde. So if you are not sure about your cost estimate, do more look ahead. Okay, and this is what is actually the case when you play some complicated games like chess or Go. It's so complicated there your cost estimates are not very clear, and there they do a lot of look ahead, bigger look aheads. So of course there is a trade-off. Bigger look ahead has some cost, right? So you don't want to kind of do a lot of look ahead as well, because the program will be very slow. So it really depends on the problem. If it's a parking problem, you don't want to do too much look ahead. But if it's as complicated as chess, then you may want to do, because even your cost estimates are not very clear. So look ahead depends. When your estimates are really bad, go for more look ahead. So basically the idea is again same as what we did before. As the L grows, your cost function approximation becomes better and better. And as I said before, AlphaGo chess does a lot of multi-step look ahead. And look ahead also helps you to fortify the stability of the policies. Okay, so you don't want to get into some bad policies so that your cost estimates go very out of range. Like the way we define a stable policy is when the corresponding cost is like finite. So in some cases good multi-step steps helps you kind of keep it stable. We will see one good example. So few things are going like very high level right now, I understand that. So in the infinite horizon case, this is what we are trying to solve. Basically, we are trying to solve the so-called Bellman equation in the infinite horizon case, and J tilde is our some form of like, although approximate, but some form of like a cost estimate. Now, when we are trying to solve problems like these, this is sequential decision making framework and infinite horizon. So this is the problems. These are the type of problem we are solving. Where are the approximations I can do, right? So here, what are the possibilities? I can approximate the cost, so which is our J tilde. I can approximate the way I do the averages, because this is expectation, and in stochastic case we have this random variables W over which we are supposed to do the average. So what type of average you are going to do, what type of cost approximations you are going to do, and how you are going to minimize solve the optimization problem. So what are the three things as you implement your algorithms? What are these approximations we are going to do, right? So let us see some of these. Like we already know a bit of these things, but so yeah. So in the infinite horizon case, as we have seen, there is a need of a singular approximate cost function j tilde. Okay, so that's how infinite horizon are. Jn converges to some j. So there is one j tilde cost. It's not like in the finite horizon case. I may have like j1, j2, j3, jn. Here we think of some j tilde, and so we may do some approximation of these cost. Obviously, that's what we have been talking about so far. So this approximations, it can happen through rollouts. We have seen. If it becomes more complicated, then we even employ some kind of a neural networks and things like that, right? And then the second one could be approximation in the averages. So if you're sure sometimes to take certain values of w, which you believe is like okay to take, although it's a stochastic variable here, but if you are sure that you can, if you're sure that some samples are good enough, then this might reduce the computation in the expectation case. Like in some stages, you believe that that I really don't need to look at various w's, then you fix one w because it's not going to affect the cost. So then in those cases, you might kind of take some deterministic values for those, although they are the random variable, but for certain stages, maybe they really are not behaving like random variable and so on, right? So it's possible to kind of substitute them with some deterministic value, depends on the problem at hand. So, and a simplification of the minimization problem, right? So can be simplify the minimization problem here, and how easy or difficult it's going to be. Now we will see this optimization problem really becomes even more interesting when we go to multi-agent optimization. In multi-agent, what will happen is that each agent will have their own control. So like first agent control is mu1, u1, second agent control is mu2, and so on, and mu m. So then if you think of this optimization as joint optimization over the controls u1 to um for m agents, then it's really very, very intractable problem, because you have like m simultaneous optimization problem. So can you kind of is it like okay to sometimes do some approximations there, right? So should I treat this as simultaneous optimization problem? Then the optimization problem is really really difficult, because I treat u as one m-dimensional vector, and then it is way more kind of a difficult problem to solve compared to if I'm doing it scalar one by one, right? So so we can do that in some cases where and it won't affect the outcome that much. Okay, if the agents are not really closely tied to each other, then in those cases it should be okay. It's not the optimal thing, but it should be okay. So we will see some examples of that, not today but in the next class. So so these are the three approximations you think of when you implement algorithms. Now terminal cost approximations, this is indeed the whole point, that we will go through some of these, but there are a few other ways we can think of, like using some decomposable structure in the cost. So is there a way to decompose this into smaller, easier cost? Can we reduce the state space dimension? This is something I have talked before. When let's say we are playing the Tetris game, then state space is like 2 to the 300, and it is really not possible to define pointwise for each possible state variables. So we need some kind of reduction into some feature space which is much smaller than the ambient space space. Optimizing certain constraints. So if it is a constraint optimization problem, which is possible, so if you work on constraint RL, then you may have to provide some constraints on it could be on the control. So there will be only restricted set of controls you will be allowed to have, or restricted set of states and so on. So So those constraints sometimes may be relaxed. Overlooking various uncertainties. This is something I have just described again. So uncertainty for us is coming from the blue eyes, which are the disturbances, and can you ignore sometimes? So that might reduce the complexity. So there are many ways to look into this. There are things like aggregation. So there are multiple states. Can you do some kind of clustering of the states, which is similar? I mean, well, not very similar, but yeah. I mean, one thing is feature extraction. Another thing is like group similar states and treat them as one state basically. Okay. So if there are similar things, there will be one. So you cluster them, and then there will be one representative state for that cluster. So that will be aggregation. So we'll look into some of these. So aggregation could be one possibility of approximation. Basically, it's clustering of states. So yeah, online simulations and all this could be done. I will skip some of these because they will be kind of repetitive. So this is what I mean by extracting features.
The goal of the Atari project was to take a suite of Atari video games and attempt to learn how to play them with an artificial agent. They are set up to try and optimize this reward signal, which in the case of Atari is the score, and do whatever they can to maximize that. So here we have a DQN agent attempting to learn the classic Atari game Breakout. It's not doing so well so far. It's missing a lot of balls, but it's getting some points, and you can see the reward ticking up at the top. Fast forward a little bit in training, and we can see that it's learned a reasonably good strategy. It's bouncing the ball up there a lot more often, but it's still not getting a very high score. It's not getting past the first few levels of blocks. At the moment, it's learning to stay over on the left-hand side of the screen and dart out just in time to hit the ball. At this point, we have a quantum leap in performance. The network learns to tunnel, as we say, that allows it to accumulate lots of points very, very quickly.
If I'm playing an Atari game, I think if you are familiar with this, then again the state space could be very huge. And the paper published by DeepMind, what do they use? They use CNN, which we know is a good feature extractor from images, and then it will kind of identify what are the good features to extract from these. Okay, so it will look into the images. Now for us, when we play this game, obviously we are also looking at the features. So the whole point of this Atari game is that this point goes and hits some bars here, and then once it hits, then some portion of the bar, it depends on the game, some portion of the bar gets like eliminated, and then it after doing that, it comes back. So it comes back like, so after hitting this, it might go here, and then here, then here, then here, and then at some stage it might come back, and then you are supposed to place it somewhere here so that it hits this. Now depending on the angle, so these are like physics simulators, they do this, is what angle, and then it might go this way, and then it will hit this, and then it might come back, so you have to move this. So this is the control you can take, right? So you have to move this. So this is the action or the controls that you are supposed to do. So you can only go right or left, and you can go like multiple right or multiple left, right? So again, just like I mean, not just like, but like the Tetris game, this has different set of controls and states, and if we apply CNN on this, then it will kind of identify what are the good features, and depending on how you keep this, you may also deviate this the way it bounces off these. Okay, so you may kind of force it to kind of go to the area where it needs to hit. So the latest ideas that goes around this is that this is a sequential decision making problem. You have states, you have actions, and then but then to understand what is useful here, let CNN kind of see this and figure out what are the good set of things, features here. Okay, so again, we don't wish to kind of encode this into a very high dimensional state. And this is what CNN will do, right? CNN takes an image from high dimensional feature space to some important features, let's say, so that it can identify flower. So flower has some, depending on the latent space, feature space, if it is like 10, then it will, so it will take an image which is much higher dimensional, but then after doing all those convolutions and so on, it might bring down into 10 useful features, and then just based on these, then you may have a classifier. Based on these 10 features, the classifier will decide whether it's a flower or not. So although the flower is coming from very high dimensional space, from the flower it could find out what is important set of features, which could be only 10 dimensional, and then it could predict. And this is something what we are also trying to do in here, right? So all these high feature spaces, you can use CNN also here. Okay, so how this will be reduced to, and you don't even have to identify precisely what are those features. Let's see, just like the features identified by CNN to identify a flower is not really not really precisely told to us, right? CNN figures out what is important. Okay, CNN by itself figures out what are interesting features.
Here, we're looking at 25 filters from the first convolutional layer in the first convolutional block of the network. So it looks like most of these have encoded some type of direction or color in them. In this one, we can visualize the vertical direction. And similarly here, we have a diagonal direction in one way, and then another opposite diagonal direction here. Let's skip to another deeper convolutional layer. We're going to choose the second conv layer from the second conv block. Here, these visualizations have become more complex and a little more interesting in regards to what types of patterns some of the filters have encoded. And now we're going to continue looking at some examples as we go deeper in the convolutional layers of our network. So now we'll look at the second convolutional layer from the third convolutional block. Again, getting a little bit more complex and a little bit more interesting. Now this is the third convolutional layer from the fourth conv block in the network. Increasingly more complex, increasingly more interesting. And then the last one we'll check out is the second convolutional layer from the fifth convolutional block. And this fifth block is the last block of convolutional layers, so you can see it has kind of the most complex encodings in it. So notice how with each deeper convolutional layer, we're getting more complex and more interesting visualizations. This whole visualization process was pretty fascinating for me when I first observed it, so I hope you think it's just as cool.
So same will happen here. If you apply on CNN will figure out what is important here. In this case, the CNN will try to figure out like these gaps. And I'm just predicting here, right? What's in the way CNN will find out, we don't know precisely, right? But what it may find out is that okay, there are gaps here, there are gaps here, there are gaps here. So it will treat it like an image, but then so on. So there are gaps here, and it will keep that in mind, because one of the things in Atari game is when you use this in a good way, then sometimes you can force this to go in some narrow area inside, and it is better to force it in that way, because then it will do a lot of bouncing off, and it will kind of eliminate all these. It will eliminate all this, and all this, like most of these. So this is what they found when they implemented this algorithm, that actually the RL algorithm could figure out that it needs to send in these narrow area where it bounces off so many times that it kind of eliminates this block very quickly, rather than you do one at a time. Okay, it bounces off, then you do one at a time. If you can figure out how it can go inside and then do a lot of things.
At this point, we have a quantum leap in performance. The network learns to tunnel, as we say, that allows it to accumulate lots of points very, very quickly. It's hard not to have paternal feelings about these agents. I remember watching with great excitement the point when it finally managed to get the ball to bounce up to the top of the screen, an agent starting to learn things that you didn't tell it. The agent will ultimately surpass the ability of a person. So it doesn't have the problem of reaction time. Once this thing is finished training, it can get a perfect score in this game, which is nigh on impossible for a human.
So, figuring out this itself is a skill, or what we call is a policy, right? So over the time, it will figure out what is a good policy to kind of do that. So at higher level, when you play this game, you identify this pattern after some time, like not immediately. Your immediate base policy is to just eliminate this. Then it comes here, then you eliminate this. Your even very simple base policy could be like, just don't let this guy fall. Okay, so that's like if you play this first time, then you realize that okay, because otherwise its game is over, right? So if it just goes and if you misses this, then the game is over. So that's like beginner level policy. So you make sure that somehow it touches this and it goes up. And then the next improved policy is like the way you make it force, right? Because if if it is coming here, if you put this here, then it may go this way compared to if you put it this way. If you play this game, you will know what I'm talking about. So this is the way you keep improving the policy, but what is important is to learn more insights, and these more insights you gain by learning some interesting features. In this case, where are the gaps and so on. So what is the in these cases, CNN is almost always applied. In chess it's applied, it's in Atari games, Atari games are of many types, and then Tetris it's applied. So these are automated thanks to deep learning. Again, RL is interesting because of deep learning, okay, because deep learning can identify features, complicated features. So deep RL is what is becoming interesting, right? So all this will go into a step where you have your usual features could be a pixel domain, but then it goes into some much reduced. So this could be your first step to approximate the feature space, which in this case RGB, and if you look into 0 to 255 and looking at the dimension of these are like very, very high dimensional space. And then you go into some very feature space, which is like, let's say, only 10 dimensional vector, but in this case it may be like million dimensional vector. So this, in my opinion, apart from all the algorithmic tricks that we will do, this is the most important thing in RL. This is the most important thing, and thanks to neural network, this is helping us, because the most important thing is to extract features, and that too automatically, because I don't want to explicitly say or code this in an algorithm. What I found is interesting. If it's doable, I will do, but then things are so complicated that I want an automated way to teach those features. Okay, so features becomes the key, and that's something we will do, just like also in the Tetris game. So now let us work with problem from control theory. Like my goal is to work on in this course, my goal is to like do more of like wider variety problem and not do only RL stuff. So control theory is like one way where you see a full view of full view, in the sense like you can explicitly see what is the value iteration, what is the policy iteration, and so on, and what stability means. So let us solve a linear quadratic problem in the infinite horizon case. So our objective is to understand the character of the Bellman equation, its approximation in the value space, and the value iteration and policy iteration in it is a continuous space problem. The system is linear with there are no constraints on the constraints on the control. The cost function is quadratic. We have seen that before, but then we will do it in a full-fledged and infinite horizon case, and it is solvable analytically, because in general you will see that these cost functions and these policies are not necessarily in closed form. Okay, so if you parameterize also by neural network and so on, but by closed form we mean that there is a formula and we can see that formula. Okay, but in general for complex problem you will apply some kind of approximations or Monte Carlo simulations. So there you don't explicitly see kind of a closed form expression, right? So here we will this is one of the problems where we will have that. So in general a linear quadratic optimization problem may look like this. So this is a little bit higher dimensional than what we saw before. We will go back to one dimensional, but in general we can think of a new state is generated by matrix times a xk plus some b times uk. So in the cruise control, and we had that we had some b uk, small b uk, which was scalar, and a was scalar, but a generic one will be a is a matrix and b is a matrix, because x itself is a vector and u is a vector. So but we will eventually solve this for a scalar valued only. So cost is quadratic, and the quadratic cost may look like this. Okay, so earlier in the cruise control we saw that the cost was like this, kx square, which is quadratic, and so this was kind of simpler. But then if you go to kind of a higher dimensional states, then you have to write like x transpose qx, and then X transpose RU, and so on. Okay, so let us go directly to the one-dimensional case and try to solve this. So one-dimensional version of linear quadratic problem is like this, where the new state k plus 1 comes from old state xk plus some control is applied. And B and UK dimensions are such that that it matches the dimension of AXK and so on, right? So if it's a velocity, then kilometer per hour, and the B and U dimension will be such that it's kilometer per hour and so on. So we don't worry about that for the moment. So this is the equation: xk plus 1 is axk plus b uk. The state is xk and the control uk are scalars. The coefficients a and b are scalar, and b is taken to be non-zero. And let us look at the undiscounted cost, because we know that in a infinite horizon case, the way we write down is xu, something like that, where we had a discount factor here, but we don't use that here in this model. Okay, so that's my choice. So it's we don't use that, like that's my choice, but then I do hope that I don't get into trouble, right? So let us assume that we don't have that discounted undiscounted cost, and q and r are positive scalars. So one dimensional case provides a convenient and insightful analysis. We can the high dimensional case is also completely solved, but in this case we will kind of look at the smaller one. Okay, so let us derive. So what we claim is that the optimal control will be of this form. J star is equal to we will prove this, right? So we will derive these things, but for the moment let us assume. So what are the results in this? So optimal cost is J star is of the form k star x square, where k is given by k is equal to fxk, and where fk itself is given by this. So basically everything is like kind of worked out, but what we find here is that k is given in some recursive expression, right? So k is equal to fk. So this is something we will try to derive, why k is like this. And then the policy is given by the optimal policy is of the linear form. So mu star is some L star x. So as we can see, policy is linear in x. Okay, now what is L star also we will derive. So the L star is given by this. So as you can see, this is a control, this is a sequential decision making problem where xk comes is generated like this, and where the cost is given to be like this. And in this case what we are claiming is that the optimal cost we could derive. Okay, for this problem we could derive the optimal cost, and we could derive what could be the optimal policy. But as I said, in general it's not easy, and we could derive in closed form. So it's closed form in the sense like I can see clearly what is that optimal cost expression here. So it's k star x square. But if I told you that j star x is some neural network or CNN or whatever, and then x, and then some neural network weight, this is not really in closed form. Okay, so we call this not exactly as closed form. So this is what we mean by that. In this case we can explicitly see the variables and so on. And this is also like here we could have some neural network and maybe combined with some simulations as well. So for the simulations I cannot write down in explicitly in closed forms, because it was based on some Monte Carlo estimates and so on, right? So this is a problem where we have things clearly written down. What is the policy? What is the optimal cost? Okay, so let us derive this. So what we know from the Bellman equation, because this is the infinite horizon case, so we have to solve the Bellman equation. If you want to find the optimal policy and or the optimal cost, if you can solve the Bellman equation, then you have that. Okay, so like theoretically you have, in this case we are lucky that we can do that, but otherwise Bellman equation remains typically kind of theory stuff, but in practice it may not be easy to solve. So the Bellman equation that we have is given by this, where our current cost is given by this gxu. So that was the cost, and then the cost for the remaining set of states will be j of ax plus bu. Now so what we have to claim is that j star that we said here. Now our claim is that j star satisfies the Bellman equation, and since j star satisfies the Bellman equation, it's the optimal cost. That's how we will claim. And then we will also claim that the optimal policy, if we choose our policy to be mu star, then it attains the above minimum. When j equals to j star. So that way we prove that this is also an optimal policy. So let us try to show these two things. Okay, optimal policy and optimal cost. Now our cost is given by kx square, and this kx square, so if we use that cost in the, and we substitute it, and then then basically we have this here. So the cost is of the form kx square. The only thing we don't know is the optimal variant of this cost. We know it's kx square, but what is that? Right? What is the optimal cost? That we don't know. So so we substitute it in the Bellman equation, and then we are supposed to minimize this. So this is a classical optimization problem, and we are supposed to minimize in u. So let us do as we did before. Before we even have had disturbance W, that is not even there. This only thing is that the infinite horizon is there. So as we can see, this is a minimization problem in u. We take derivative with u and equate to 0. So we did that. So this becomes 0, and this becomes 2RU, and here this becomes 2 times of this guy, and then the derivative of this guy b. So the one b shows up here. So this is simple stuff, and then we solve for the u, because this is a minimization problem u. So we find an expression for u from here. If we do that, so if we do that, then we get u is lkx, where lk is minus ab k by r. So basically lk has been written, those expressions are kind of written in terms of lk. So it's very easy to kind of solve for this here. So we take u common, right? So 0 equals 2r plus 2b k, b square k. So this goes with u plus 2b k a x. Now, so this implies u is minus 2b k a x divided by 2 also we can take common, r plus 2b square k u. 2 gets cancelled. So it's like minus. So L will be, so L should be like this, right? This is like this is our L, right? B k a and so on, right? So b k a minus, right, and plus r plus b square k, r plus 2 got cancelled, right? So r plus b square k. So that's what we derived. So L mu is lkx. Now we will substitute this control, which is our mu lk, in the Bellman equation, because for this L it got minimized, right? So for this u, I mean, it got minimized. So we will, since we minimize this, we found the mu for which it's minimized, we will now put it back in LQ9, and that will be like the optimal cost. So we substitute this, then the expression in LQ9 becomes this, which should be not so difficult to identify, right? We have q, okay, we keep this in lkx. So u, we replace u by lkx. Right, so we replace u by lkx, right? So this is right. So this is the u for which it got minimized. So I substituted that, and this should give me the optimal cost, right? So then I guess we will, so then everything is in x. So we will take x square common. So this is q plus r lk square plus k, and then a plus b lk square, and whole thing multiplied with x square. I took x square common. So as we can see, the cost is a function of x square, right? And with this term that we have now, okay, so it is, the optimal cost is indeed quadratic. So that we can call this as a q plus r l k square k a plus b l k. We call this is exactly what we derived, an x square outside, and we call this as fk. Okay, this constant, not really constant, like iteratively it will change. So then our cost, the optimal cost is of this form, which is of the form jx is f of k. So it's like a function of k x square. So here f is given by but what we know is that the cost that we had was of this form kx square, and what we found out is that this cost is of this form fk x square. Okay, so we equate that. So j so we equate j equals to kx square with the cost that we found now, which is supposed to be kind of optimal, and from there we will get a recursion for k. So this goes away. So after cancelling out x square, so we get k equal to fk. So k equals to fk. Now we substitute what was fk before, right? So this is our fk. So then we get this equation k equals to something in k again. Okay, this is a function of k. This equation is termed as Riccati equation, and f is called the Riccati operator. This operator could be in terms of metrics and so on if you do the higher dimensional quality control, but since this is a scalar case, you see that fk is a single scalar. K is like a scalar, right? So the policy which corresponds to k star will achieve the minimum in the Bellman. So if we look into the picture, then this is the picture. The optimal cost function is given by k star x square, and k star is given by the fixed point equation k equals to fk. So we are kind of supposed to solve this. So this whole problem kind of boils down to solving a fixed point equation, right? So fixed point equation is like fk is supposed to be equal to k. So this is like saying that intersection of, so k equals to fk means intersection of line, you can say y equals to k, and maybe it's a curve, not necessarily a line, of the curve, some another curve which is y equals to fk, right? So basically we are supposed to have a line. So this line is like a easy line that goes through the origin and 45 degree. So this is what you see, this line, which is y equals to k line. And if you plot the fk, which is not necessarily line, fk is of this form. So this is the red curve that you find, and the solution of k equals to fk is the point where they intersect. So where the line intersects with this fk. So this is the optimal k star that we are looking for. Okay, so so that's it. So here, so what this is also trying to say is like where because this, if you look into this k, this curve and the line, it is intersecting here, but it is also intersecting at these places. It turns out that these ones are like kind of unstable, okay, compared to these. So there are two intersection points. The one that we will take is this. Okay, so here f is concave. If you look into the function f is concave, at least from the figure you can see that it's concave. It is monotonically increasing. It is increasing over minus r by b square to infinity. So minus r by b square is like here. So from here to here it's infinity. It tends to flatten as k approaches infinity. Yeah, so this is also we saw here. So it is kind of flattening out here. And the quadratic Riccati equation k equals to fk has another solution that we just saw, which is like intersection here, k bar, and which is negative. So since it's a negative, in our model it's like negative cost is like not really relevant in our case. Okay, yeah, with the type of problem we are solving, we will discard the negative ones. Okay, and let us look at the at the policies which can make this unstable, the cost will go up to infinity basically. So so the policy is like mu is Lx, and we will say that the policy is stable when it satisfies this. And one reason for this is that as k tends to infinity, because xk plus 1 is related to xk in this way, if this is less than 1, then kind of it will make sense, because then xk converges to 0 as k tends to infinity. So the cost function again can be written in this form, where k solves this Riccati equation again. So with this type of policy, which is explicitly given in this form, a plus bl xk, and then for this we can explicitly write down what will be our f, and the corresponding Riccati equation, we will say it corresponds to the stable policy mu equals to Lx, and this is linear with respect to in k. Right. So this is the plot for the stable and unstable case, right? So for the stable policy, we have this, and if it is unstable, then this is the plot for that. Okay. So if we have a stable policy, then we hit this line here, which is pretty close to the optimal policy, we can see here. But if you follow this policy, then it will be very far away from k star. So in terms of algorithm, if we run a policy iteration in this case, then a stable policy will let us go towards optimal k. Yes, I think I'm missing the equation for the policy iteration, right? Yeah, k equals to fl, right? Yeah, k equals to fl, right? So we already have this. So what we are supposed to solve is k equals to fl. So fl is this line, right? And this is linear in so policy iteration is interesting, right? It's linear. Now we are looking at this line intersecting with the k line, right? This line intersecting with the k line. This is policy iteration. And the value iteration for us was the red line intersecting with k equals to fk. So that was this point. But if you run the policy iteration, then basically you have to find out where this line flk is equal to k. So basically flk intersecting with this, which is this, right? But if you look into this, right, this unstable one, then it intersects the line in the very somewhere here, I guess, right here. It's like very far from k star, because policy iteration at least is like very close to the k that I find from value iterations. So here with this example, you see both the views, value iterations, how it looked like. In this case, the red curve intersecting with the line. So obviously the algorithm is a bit different one here. And then policy iteration is as if like two lines intersecting. Okay. And how will the fixed point, how the fixed point iterations look like in this case is you start with some, like you may want to solve this iteratively, right? You, in this case, it is easy to say that look at the intersection point, right? And where there is the solution, right? But in practice, we don't do that, right? We start from some initial guess, and then so the way the iteration will proceed is that you will start with some initial guess, right? And then it will go like this, hit this, then it will go like this, hit this, then it will go like this, hit this, and so on, right? This is the iterative way the fixed point iterate will start. You will start with some initial k node, then k1, then k2, and so on, right? And if it is the curve, then you will start from some initial k0, it hits this curve, then you are here, then it hits this curve, then you are here. So that way fixed point iterations work, like step by step. That's why it works, right? Now, if you initialize this somewhere else, like if your initial step is like somewhere else, like yeah, so you might end up like this. It will you will deviate towards a bad bad in the sense like that that negative k. But if you are here, then the way the curve is, it will force you to go like this. But if you are somewhere here, then you might end up like this. Same thing goes with this policy iterations, right? If you start somewhere here, then it is forcing you to go to this fixed point. But if you are somewhere, I think the policy iteration seems quite stable, right? If I start from here, yeah, in that way it looks very nice. You see, policy iteration, even from here I'm trying to initiate, and it is forcing me to the correct one. So it depends. So algorithmically, from where your initial guess will be to solve equations like k equals to fk, value iteration, or k equals to flk for the policy iteration. So initial guess also matters. Okay, so I will wrap up with this. So what we saw is a full value iteration and policy iteration for quadratic control, linear quadratic control LQ problem. And we saw some policies are stable in the sense that if I solve the fixed point with those stable policy, I go close to the k star, which is the optimal cost. If not, I will deviate, obviously. So this is the problem solved by control theory community in a full form. They in a exact, almost like exact form. There is no real approximation here. So there are problems where we can do this value iterations and policy iterations in a very clean way, like we did it here. But as we will see, the real life is not that easy. Okay, so we won't be able to kind of do this in such an easy way, right? Okay, so that will be all.